Welcome back, everybody, and welcome to the second part of this course, which is about generative models. And I wanted to repeat some of the things which we discussed in the very beginning of the semester about generative models. And so that means I want to give you an overview of these models. And one of the important things which comes into play here is Markov chains and Monte Carlo simulations. And this is what actually made the big game changer for many of these methods back in 1990s, 2000 roughly. And this is also something which gave a renewed interest in Bayesian statistics. So these things are very much interconnected. So that means that today I will also give you a short review of Bayes' theorem and the probability distributions, because we will deal with quantities like conditional probabilities, marginal probabilities, and other quantities which are tightly linked with Bayesian statistics, but also statistics in general and probability theory. And then the first model which we are going to study is the Boltzmann machine and so-called energy models. And you will recognize, for those of you who are physicists and have had a training in, let's say, statistical physics and statistical mechanics, you will recognize many of the topics here. So we are going to deal with a probability distribution, which in the beginning is going to be given by the Boltzmann distribution. And these are often called energy models. And I will try to explain why and where we have the bottleneck. So today is going to be a kind of background theory-like lecture. And then next week, we will look more at implementations of Boltzmann machines. And the chapters 16 and 18 contain a lot of the background information for Boltzmann machines and also this kind of generative models. So they are very useful introductions to the topic themselves. And chapter 17 gives you a review of Markov chain Monte Carlo methods. But I'm going to remind you of some of these technicalities. And with Markov chains and Monte Carlo methods, this is the way we are going to sample the different points. We are going to look at two different ways of accepting one specific new sample. One is called the metropolis sampling, which many of you probably have encountered when you studied at least computational science courses, computational statistics, computational physics. But then the metropolis sampling is actually a way to sample which requires you to be able to sample from a multidimensional probability distribution. So metropolis sampling in this kind of machinery is normally not used because it's computationally very demanding. So what that is replaced with is something which is called Gibbs sampling. And we are going to revisit these methods. So we are going to pay some attention to specific technicalities, which then will allow us to make our own implementation of, let's say, a Boltzmann machine. Now, I wanted to say a little bit about generative models and where we have the big distinction. So we mentioned some of these things before when we began the semester. So for many of you in project number 1, you've been dealing with what we normally call discriminative models, which means that we have data which often are labeled. They don't need to be labeled, but the idea then is that you take some observations and then you want to train a model through a specific algorithm, which then is able to make predictions and which is able to classify whether this is a horse or not. Now, what we are going to do now with generative models is that we will essentially produce a probability distribution. And with that one, we will generate new images. So it doesn't mean that we train a model to reproduce what we have and to be able to make predictions of what this could be. But now we actually want to have a probability distribution which is going to make, let's say, new horses for us. So this is the basic foundation for many of these generative models. So instead of training like in a regression type of problem where we want to train a function which we then use to make predictions and eventually find correlations, we are now going to train a probability distribution. And with that probability distribution, we are now going to generate new samples with that one. So the philosophy is a little bit different from what many of us are used to when we look at the standard discriminative models. So these are figures and text which I put back here and which we discussed in the very beginning of the semester, where we also have a distinction here between discriminative models and generative models. So as I said, with a descriptive or discriminative model, what we typically have is some training data. And in this specific case, we want to train a model which tells us whether this is a Van Gogh painting or not. So that's a typical example of a classification type of problem. So you could train on images of bridges, and then in your model, then you will be able to discriminate between different types of bridges. And that's the basic idea with discriminative models. So there is a nice figure which I took from the textbook by Foster. And when we look at these generative models, so let me just shrink the size here a little bit. So we typically have models which deal with the explicit probability density. And one of these models where we now have an approximative density are so-called energy-based models. And these are models which we will discuss. We will also discuss variational autoencoders. So before the Easter break, we discussed autoencoders. And we went through the mathematics and discussed the autoencoders in terms of dimensionality reductions. Now we are going to also extend upon what we did after we have discussed energy-based models. And then we will also discuss diffusion models, and we have the implicit density approximations, which then give rise to generative adversarial networks. So the rest of the semester, we will focus on variational autoencoders, energy-based models, Boltzmann machines as a classical example, GANs, generative adversarial networks, and then we will also look at diffusion models and say something about stable diffusion models, which are some of the more popular methods nowadays to actually, for instance, generate images, generate music, or whatever you want to generate. And if you go into many textbooks, you will see that even if they haven't been able to catch up with the recent developments in stable diffusion models, you will see a lot of mention about diffusion models. So this is roughly what we will do for the end of the semester, till the end of the semester. And the kind of idea behind Project 2, for those of you interested in that, is that we can use variational autoencoders and Boltzmann machines, energy-based models, and eventually GANs, and replace, in case you've been dealing with classification problems or regression type of problems, to replace those calculations you did in project number 1 with these generative models. And again, here you will find, when you just search for it, you will find extensive examples in using both TensorFlow and PyTorch for all of these algorithms here. So we have the textbook by Foster, which essentially gives you many of these algorithms written with TensorFlow and Keras. And then in the textbook by Babak, you have a pretty detailed library with PyTorch. Okay, so one of the things I wanted to do now is to remind you a little bit about statistics. So I'm going to take the liberty in the beginning now of using the slides here. And essentially because I wanted to remind you a little bit about Bayesian statistics. So Bayesian statistics, or Bayes' theorem, is a very, how to say, hot field of research. Because as we mentioned in the very beginning, if you look at most of the deep learning methods, we are often not interested, or we're actually not aiming at finding a probability distribution unless we deal with generative models, which means that what you do typically with a CNN or an RNN or deep neural network is simply to be able to make a predictions. So you've been making a fit, you can make a prediction whether this is a bridge or not, and you can find correlations in the data sets. However, with Bayesian statistics, and also the topic which is a pretty brand new research field, which is called Bayesian machine learning, you're trying then to produce a probability distribution. So here we will produce a probability distribution with generative models without mixing too much of the Bayesian statistics. But this can be done if you want to. So typically what you have, and Bayes' theorem is the basic starting point. It's extremely simple. So you have to simply have seen some of the basic axioms in probability theory and statistics. So, and it plays the same role as Pythagoras in geometry. So if you now have two likelihoods, you have two events, two domains of events, one which I call X and one which I call Y. So these are the different possible events which you can have in this domain of events. And in this case, we have two probabilities, P of X and P of Y. And the likelihood for a specific event is something which later I will just simply replace with a shorthand notation. But we have the union of events. So this is something you will find proved in standard textbooks and statistics. So the union of event is actually the probability of X plus the probability of Y minus the probability of not having X and Y. And then we have the product rule, which is simply given, and this is something which I have to remind you of when you see this bar here, this vertical line. This is called the conditional probability. So this is probability of X given Y multiplied with the probability of Y. Alternatively, you can rewrite this as a probability of Y given X multiplied with the probability of X. So these are some of the basic theorems which you probably have encountered when you look at statistics. And if these events are independent, which we will often use, that means that we have independent and identically distributed events. So if these are identically distributed as well, then these P's are the same. And then we can simply write this, the product rule in terms of the probability of X and the probability of Y. So you've probably seen these things before. And then there is a very important quantity which we are going to use again and again now. And in particular, because we are going to have probability distributions which are given in terms of parameters we want to optimize. And then at the end, if we want the probability of X, we have to integrate away or sum away all the intermediate variables which we have defined. I'm coming back to this. But the so-called marginal probability is the one where I'm now summing up over all the other variables except those I'm interested in. So if you have a probability distribution, for those of you familiar with the Boltzmann distribution, this could be depending on the energy of the system and some parameters. If we then integrate away the parameters, then we have the conditional, the marginal probability with respect to energy only. So these are important quantities which we actually are going to use now quite a lot. So just keep this definition in mind, the marginal probability. And with a marginal probability, we can also define what is called the conditional probability. And you see now that this in a way looks almost like a kind of normalization factor. So the conditional probability of X given Y is obviously given by the product rule here. So if you go back to the definitions which we have, this definition which we have here, Px and Y, which is given by this quantity, you can then define the conditional probability. Now, pay attention to this expression here, because that's the one which enters Gibbs sampling. And when you look at the conditional probability, often your probability distribution becomes simpler than you sampling from the full probability distribution. So just to give you an example, if you have a quantum mechanical system like atomic neon, so atomic neon, if you're only looking at the electronic degrees of freedom, you have 10 electrons in 3 dimensions. So that means that if you want to describe a probability distribution for finding these electrons in specific positions, this is a 30-dimensional object. And even if somebody was to give you an analytical expression for it, which nobody still has been able to cook up, unless you have some approximations, you would have to sample a 30-dimensional object. So I'm mentioning this now because it becomes important when we are looking at the way we do the sampling in these models with Markov chains, because if we were to do a metropolis sampling, we would have to sample a 30-dimensional object. With a conditional probability, we can often reduce that dimensionality. So we're coming back to this. So I'm just bringing up these definitions because they are important technicalities, and you will see why then a sampling rule like Gibbs sampling is the one which is used when you do either Bayesian statistics. So in Bayesian statistics, to be able to do a Markov chain Monte Carlo calculation is actually the basis for Bayesian, or I shouldn't say the basis, but it is one of the reasons why people use Bayesian statistics. So the way Bayesian statistics was introduced for many, many years ago was that you had probability distributions which you could manipulate analytically. But there's a limit to how many of these probability distributions you can manipulate analytically. And therefore, numerical sampling and the numerical production of a probability, a final probability distribution, is something which is facilitated by Markov chain methods. And the sampling is then given by typically by Gibbs sampling, which we will come back to. Any questions so far? So Bayes' theorem is actually us taking this conditional probability and the marginal probability. So this expression here, which you then recognize here again, which is the marginal probability and the conditional one. And then if we take these two quantities, we can actually rewrite it like this. And this is essentially Bayes' theorem. So you can actually find the probability of X given Y in terms of the probability of Y given X. And what you need then is a model for this quantity P of X, which in Bayesian statistics is called a prior. This quantity is called a likelihood, and this becomes a normalization constant. So this is a normalized probability. You can interchange X with Y here, and then you will simply have the probability of X given Y multiplied with the probability of Y. So you would have a model for these quantities. So it sounds like Bayesian statistics in a way solves the problems for you, but it is a approach which depends on you having defined a model. So a typical question which you could have then is, if you take the example of where I live, I have, 5 buses plus a subway, which brings me downtown or to the university. And I could give a same likelihood or the prior to all these options to get to the university. And then I would have a likelihood, this P of Y of X, for actually getting here. And then I would normalize it, and that would give me the prior or the final probability, which is normally called the posterior probability for getting to the university, given all these selections which I had. So the best way to look at it is actually through a simple example, because that gives us a better understanding of Bayes' theorem. So the quantity which you see Py with a given X on the right-hand side, that is normally evaluated for the observed data Y, and it can be viewed as a function of the parameter space represented by X. And it's normally not normalized, and it's normally called the likelihood function. Whereas this P of X on the right-hand side is called the prior, while the function on the left-hand side is the final probability which you want to have. And the denominator which you have here serves as a normalization factor. So there is a simple example which I often like to use. And this is an example which, when you look at the initial probabilities, it can actually look a little bit scary. So this is a constructed example from mammography scans. And then you want to rule out the possible breast cancer cases. So you can define the sensitivity for a positive event by a variable x, and that takes binary values with x equal 1, representing a positive event, and x equals 0 being a negative event. And then you can reserve y as a classification parameter for either negative or a positive breast cancer confirmation. So they are both binary values. So you take x can be 0 and 1, and y can be 0 and 1. So that's the two outcomes which you have. So positive here means actually having breast cancer. So it's not a very positive thing, but the way it's used here is actually as having breast cancer. And then what you want to ask then is actually why represent the case of having breast cancer and why as not. So what you can say then is if you assume that you have breast cancer, the test will be positive with a probability of 0.8. That means that given X from the mammography, the observation you have is a positive one, and given that Y is positive, then the likelihood for having breast cancer is 80%. However, the likelihood in the population is not 80%. The likelihood in the population is fortunately a very small number. So this sounds a little bit scary, but this is not correct, because what we need to do is actually to use Bayes' theorem in order to evaluate so not x equal y or y equal 1, but we now want to use by using Bayes' theorem, we're actually going to get the correct answer to that. So this sounds scary, but you have to do it correctly. So if you look at the prior probability in the population as a whole, so you just take the whole population and you take a uniform distribution. So you take the number of the female citizens above a certain age, and then you simply divide by the number of cases. This is a very small probability, fortunately. So you need also to account when you do these calculations that the test may produce a false positive result, a false alarm. And in this case, I just put that one to a number. So these are just numbers which I made up. So this 0.8 may not be what the machine, the mammography, actually gives. And this 0.1, but these are numbers which I just made up. And then when you use Bayes' theorem, you can find the posterior probability that the person has. So the question you have to ask is not what the machine gives, but the probability that you have breast cancer given that the machine flags that you have a breast cancer. So that's the correct question to pose. And if you do those calculations, so if there is a positive event from the mammography, the likelihood for having breast cancer, when you then use Bayes' theorem, is actually 3%. And that is the more correct way of dealing with these kind of probabilities. So if you just look at the output of, let's say, a scan, and you look at this probability here, this sounds like a very scary number. But that is not the correct way of doing it, because the question you have to pose is, what is the probability of having breast cancer given that the mammography flags a positive event? That sound reasonable? So this is just an example on how you use Bayesian statistics and how that actually gives you the correct interpretation, because you are asking the correct answer. You're not just looking at what comes out of the mammography. So there's another thing which we need to deal with, and that is called the maximum likelihood estimation. And this is actually, and the kind of assumption which we normally make is that the events are independent and identically distributed. And that means that we are going to make a probability distribution, which is the product of all the individual probability distributions. So let's switch back to the whiteboard here. Oops, let me just bring up that one. So let me just switch over to the whiteboard here and say a little bit about the maximum likelihood and the kind of probability distributions which we are going to study now. So if we look at the maximum likelihood, so we have made an assumption now that all events are IIDs. Let me just quickly remind you of that, independent and identically distributed events. So we are going to have a probability distribution for some specific variable x. So we have a domain of events, and this domain of events is now given by a set of stochastic variables, x, 0, up to xn minus 1. So this is our domain of event, and these are assumed to be stochastic variables. They are independent and identically distributed, which means that we can now make a model for the probability distribution. So the total probability, P of x, and I'm going to write it like this, where theta are now parameters. So these are the parameters which we want a neural network to optimize for us. So these are the parameters. And this is now going to be given by the product of all these individual events. And then we have a P of x of I of theta. So let me just give you an example of a model which many of you have seen before. So the example which you have encountered and which we are going to elaborate a little bit more on now, this is the Boltzmann distribution. And the Boltzmann distribution, for those of you who have studied physics, is given now by P of x as a function of theta. And this is given by a normalization factor and a function which typically looks like this. A B of E is going to be a function of theta, and it's divided by a Z, which is a normalization factor. So what we can do now, so this normalization factor Z is normally given if this is a continuous function. So we would have an x, which is integrated over the domain of all possible events, if it's a continuous one. And then we also have an integral over theta. And then we would typically have a E of minus beta E of x of theta. So that's the normalization constant. So this is a normalization constant. Later, we are going to look at the value of Z. When I write C of theta, this becomes a marginal normalization constant. That is just going to be given as an integral over d of x of E of minus beta of E of x of theta. Keep also in mind that we can define a P of x, of just of x, which is now the marginal probability, okay? And that is going to be given by an integral over d of theta. And then I have my E of minus beta of E of x of theta. And if these are the discrete variables, so if discrete, which is the common case, if we have discrete variables, what we will typically have then is that this P of X is going to be a sum over all the variables theta of I, and then I will have my E of minus, or we can just write it in a more general way. We don't need to write it like that, but we could just write a P of X of theta of I. Similarly, if I look at this quantity, which I call C of theta, and now I'm just being generic, so I'm not putting a subscript I on it, that is simply going to be given by an X of I, where these X's are stochastic variables defined by the domain, which we have. And this is then going to be given by an P of X of I of theta. So I'm skipping then the theta of I constant here. So these are just definitions which we are going to use again and again. Now, if you look at the Boltzmann distribution, what we have then is that this E of X of I as a function of theta, and in principle is a function of theta of I. This is normally called an energy function because it's inspired by Boltzmann machines, where E is the energy of the system. So this is normally called an energy function, which obviously leads to energy models. And these are the energy models which we will start with now. And so next week as well, we will discuss more the implementation of Boltzmann machines. So you will see clearly how you can actually define these different types of models. And this E of X of I is now broken down in terms of an E of X. So let me just write it in a more generic way. There's going to be a hidden layer, and then we are going to have parameters, theta of theta, where these parameters theta are going to be given by biases, A and B, and weight parameters. So what does this energy function look like? So what we have now is a model which we are making. And we are going to train a neural network based on a specific approximation to this energy function. Or we can just call it a model function. But it's normally called an energy model because it's so much inspired by the Boltzmann machines. And keep in mind that this parameter beta, which I have, this is in statistical mechanics. It's given by Boltzmann's constant times temperature, but we are going to just put it equal to 1. So that means that this function, which you see here, this E function, does not have any units. So this is a dimensionless quantity. But this is just to follow the kind of inspiration from statistical physics. Now, if you then look at these type of models, there is a simple model which we're going to look at closely a little bit later. So there is called a binary model, or binary Boltzmann machine. So that means that X of I takes only the values, it could take 0 and 1, or -1 and +1. So this is up to us. So if we want to use this inspiration from statistical physics, it's pretty common to have -1 and 1. And we could have this H of I to take the values of -1 and 1. And that means that this energy function, which we defined, this X of H, and then these parameters theta, is then typically given in terms of a sum over the so-called visible nodes. I'm putting a V here to indicate that this is the number of visible nodes. There is a parameter A of I multiplied with the value X of I. There is a sum over the hidden nodes, H, up to the number of hidden nodes. And then we would have a new parameter, B of I, B of J, multiplied with H of J. And then we have the connection, the coupling between the hidden nodes and the visible nodes. So this stands for hidden. And this is visible. And then we have a sum of I and J up to V and H. and then we have some coupling constant, Wij, the weights, and then we have an x of I and an h of j. So what does this network look like? So I said we have the visible nodes, so you can think of these as the input nodes. So you could think of having a set of input nodes. So we have an x1, x2, up to some x of v. And then we have the hidden, so this is the visible layer. And then we have the hidden layer. And then we have up to some h of h. And we have an h of 1. This goes on like that. And then we can have connections between these different nodes, which we have here. And normally they are fully connected. So that means that what we would have here would be a parameter W11. So the B's, which you see here, and the A's, they play the role of as the same as the biases, which you would have in a standard neural network. So these are the so-called biases. And these are our weights. So what we are doing now is that we have a network which we are setting up. The parameters we want to optimize are these parameters here. And we have chosen a model for the probability distribution. So keep this in mind now, that we have made a probability distribution which looks like this. And now we want to optimize the probability distribution. So keep in mind then that if we go back to this expression here, this is the quantity we want to optimize. So we are going to either take the maximum probability or we can take the minimum probability. Nobody's interested in the minimum probability. We want to have a probability distribution which is maximized. So that means that we want to find the parameters theta which maximize that quantity. So in order to find these parameters and to find this probability distribution, what we are doing then is to use the maximum likelihood, max likelihood, and the theta parameters, they are normally then what we call the maximum likelihood estimators. So what we want to optimize is then argmax of theta. These are the set of parameters which we have of this probability distribution, P of x of theta. That's the maximization problem. Now, to maximize a product is something which is normally a little bit more tricky. And what we normally do then is to maximize the log of the probability. And what you will typically see then is that we would replace, and these problems are equivalent. So we have the log of P of x of theta, which then means that we need to take the derivative. So we would have delta of theta of the log of the probabilities, which means that what we have then is now a sum over all the x's instead of the product of all the x's. So we would have a sum of all the x of i's, depending on d, or the domain which we have chosen, of log of p of x of I, since we also have assumed that these x of i's are independent and identically distributed. So this is a quantity which we then want to maximize. Alternatively, since this is a monotonously increasing or decreasing function, if I put a minus in front of it, then I can have a minimization problem. So this is very much up to you. Normally we prefer minimization problems instead of maximization problems. So, or what we can do then is just to have argmin of theta And then we have minus log of P of X of theta. So these are the two different ways of actually dealing with the problem. Now, what you will see now, when we are dealing with this type of problem, what we need is to calculate the derivative of the probability distribution with respect to the parameters theta. So what does that actually mean for us? Now, what it means is something which is going to lead to some problems. And the kind of problems is something which you will see immediately now when we are just setting up the different types of equations which need to be optimized. So let us take a closer look at that. So let's now write this probability of X as a function of theta. And now I'm going to integrate away the X variables in the normalization constant. So because I'm going to take the derivative with respect to theta. So that means that what I'm going to have here is this quantity here only, okay? And then I'm going to replace this other function which I had previously, this e to the minus beta times z, with just a function which I'm calling x as a function of theta. So this is in the Boltzmann machine, this is given by e to the minus beta times this energy function. So just keep in mind that when we did the Boltzmann machines, then we are putting in an explicit expression for these energies, or for this function f. So you can actually, and what you will see now is that when we go to variational autoencoders, what will change is actually the expression for this quantity here. And this is where you can plug in the model which you're interested in. So the Boltzmann machine, like in this case here, where we assume that these are take binary values, this will be a natural choice for the model. You can replace the x's if you're looking at continuous input variables. You could replace them with a Gaussian distribution. And then you could have some x minus a squared, just to give an example. And that would fit something which runs more like a harmonic oscillator type of problem. Now, keep in mind also that when you're translating this into an actual problem, if you now are looking at, let's say, and I am still this kind of quantum mechanical person, that means that the examples which I come up with are often from quantum mechanics. But if you have two electrons in two dimensions, then the number of input nodes would be 4, 2 dimensions and 2 electrons. These are the variables which you need to specify the system. So your visible nodes would in that case be 4. If you're dealing with atomic neon and you only have electrons as degrees of freedom, then you would have 30 input nodes. And that means that your x's here would be parameters which you would use in order to train this probability distribution. And these h's which you have here are simply the hidden parameters which give you additional flexibility in optimizing the function. So you can think of this as additional parameters in the optimization of a probability distribution. So when you look at a normal Boltzmann distribution, for those of you who have seen that, you won't see this parameter theta. But this is, however, a trick which is often used in statistical mechanics optimizations, but also in quantum mechanical applications of this type of probabilities by giving you additional parameters to train. And that gives you additional flexibilities. So some of you may have heard about Hubbard-Stratonovich transformations, which are often used in statistical mechanics. These are transformations which add additional degrees of freedom and give you more flexibility in optimizing a function. So in a way, you can think of a neural network as something which gives you more flexibility in the training. And hopefully then picks up some correlations which you would not be able to pick up. So these Boltzmann machines, as we have here, they are not limited to only having one hidden layer. You can stack them, but then the training becomes more difficult. Actually, the most popular model is the one which you see here, and that's called a restricted Boltzmann machine. But there's nothing which hinders you on stacking these. Actually, Boltzmann machines back in 2010, 2011, we're just talking about 12, 13 years, were very popular as alternatives in imaging. But then convolutional neural networks took over and just wiped away all the interest for Boltzmann machines in classification of images, because they were much more powerful. But this is actually something which has been used in image classification. So if you're interested in that as a follow-up of project number 1, and you've been dealing with a classification problem, you could then implement Boltzmann machines and compare Boltzmann machines with CNNs, and then make a critical evaluation of different ways of performing a classification of images. But you see, it's very much physics inspired, and you see many, many points of contacts for those of you who have studied statistical mechanics. Now, after the break, we're actually going to look at the root of all evil here. And the root of all evil is the calculation of this guy here, and how we're going to evaluate that one. And that leads to many, many different types of approximations. And so after the break, we're going to look at the way we typically set up this problem, because what we want to do is to calculate this quantity here and drive this one to 0. So this is the cost function. The cost function is the log of the probability distribution. And the optimization problem then is simply taking the derivative of this quantity. So when the quantity we optimize is the probability distribution. So we train the system to find the optimal parameters which drive this quantity here to 0. And when we have that, then we have a probability distribution. And with that, we can quantify errors in the predictions which we make. If we want to quantify the errors in the theta, we would have to labor a little bit more. But we end up with a probability distribution which we then can use to generate new events here, which were not in the original set of samples which we had. So I hope you see the kind of overarching picture with the generative models. And the Boltzmann machines are, in a certain sense, for those of you who have taken courses in physics, they're very intuitive for us. As we discussed before the break, the Boltzmann machines are, especially in the disguise of what's normally called a restricted Boltzmann machine, what we have here, where we have just one hidden layer and one visible layer. This is a machine which has been, or a model which has been very popular in the literature. And it was actually used in the beginning of this millennium to train on image classification. But then, as we mentioned, CNNs took over and essentially wiped out all the interest in Boltzmann machines applied to classification problems of images. However, it has had a revival for many types of physics applications. And it's also one of these, from a more pedagogical point of view, it's one of these models which should give a nice introduction to generative models for those of you who have a physics and mathematics background. And one of the reasons for that is that this type of probability distributions is something which is widely used in statistical physics, but also has a quite lot of applications in statistics and in mathematics. Okay, so what I wanted to discuss a little bit more now is the kind of problems which we have to face when we mathematically and computationally are going to implement this type of optimization. So this is the main optimization. And there's a lot of discussions in the literature on how we represent this probability distribution. In particular, because this is going to be a multidimensional object, and it can be very difficult to sample from it. So we need to have efficient recipes. So we're going to look at several of these kind of ingredients, And where we ended before the break was us replacing this function and this z of theta, which is a normalization constant. And we are leaving out theta because we're going to take the derivatives with respect to theta. That means that in the optimization, what we need to calculate then is either this quantity, which is less frequent because we often have discrete variables, or we simply have to calculate x of I, element in the domain of events, which we have, of f of x of I of theta. So this function f can be the standard Boltzmann distribution, or it can be another type of model. But you see that the problem, irrespective of what kind of probability distribution model which we adopt, there is a normalization factor here, which is going to cause a lot of problems for us. Okay, so let's look at some of the quantities which we need. So we want to optimize. And this is the basic essence of a generative model. We want to optimize this probability distribution, P of x of theta, with respect to the parameters theta. And for this simple Boltzmann machine, which I put up, we had some biases and we had some weights which we want to train. So in our case, when we now look at the expression which we put up, if you look at this expression here, what we have then, when we take the log of this, is obviously the derivatives of, so this is the quantity which we want to calculate, of P of x of theta, and that becomes delta theta of log. If we now are looking at the positive quantity, I mean the positive log, and that means that we have a maximization problem. So we would then have the log of this function minus delta theta of log of z of theta. Now, this is still a function which we hopefully can evaluate, even if it's a multidimensional one. On the other hand, the normalization factor, or the partition function as it's normally called, is a quantity which we often don't want to evaluate, because in principle, we would have an infinity of samples, and we can have many parameters, which means that this quickly becomes an intractable type of problem. So how do we actually perform the calculation? So I wanted just to show you the kind of standard recipes, which is then done in order to set up this type of calculations. So let's now look at the denominator. So we have assumed that the probability, this P of x of theta, is actually given by I of P of x of I of theta. So that's a basic assumption which we made, which means that log of P of x of theta is actually now given by a sum over I element in this number of samples which we have for the domain of theta. So let's look closely at the gradient of the logarithm. So what we need now is also the log, this quantity which you have here. Let's take a closer look at that one. These things also have a name. This is called the positive phase. If you change to the negative log, it's obviously the negative phase. But this is normally called, if we have a maximization problem, this is the positive phase. And this is normally called then the negative phase. So if we then look at the log of z, so let's take a closer look at that. So which is the second term here, and the derivative of that one with respect to theta. So what we need then is to look at this quantity here of log of z of theta divided by, oh, sorry, it's not divided by. So we know that we can write that one as the derivative of c theta divided by c of theta. So if we then manipulate this further, what we have then is that this is the derivative with respect to theta, the gradients, and then I have my I elements in D, and then my z of theta. If we go back to the definitions here, if we look at that definition, we have defined this function f. So what we end up with is the log, no, sorry, this should be the derivative, it's f of x of I with respect to theta divided by z of theta. Okay, so I'm just plugging in the expressions which I have, and these expressions which I have here can then be rewritten as a sum of I elements of D, and then I'm going to have a delta, a gradient with respect to x of I of theta divided by z of theta, like that. So what we are going to assume now is obviously that this probability P of x of theta is always larger or equal than 0. That's a typical case which we typically end up with basically for all the models. So that means that I can substitute this quantity here, or not that quantity, this quantity. I can substitute that one with the exponential of log of f of x of I of theta, like that. Okay, so this is just a trick which I'm applying here. So what I get then is the following. So I have, this becomes equal to a sum of I of all the samples which I have in the domain. And then I have my d theta, and then I have the exponential, and then I have log of f of x of I of theta, like that. And this is divided by z. And now I'm just skipping theta here, just write c, of just plain laziness. Okay, so what we have next then is that I can obviously rewrite this one as, so this is simply I over d, and then I have the exponential of log of f of x of I of theta, and this is then multiplied with log of f of x of I of theta divided by z. And this gives me, when I bring it back, this gives me f of x of I of theta, and then the derivative with respect to log f of x of I of theta divided by z. Now the quantity which you have in here, so let's single that one out. This is nothing but the probability of x of I of theta. So what you have now is actually an expectation value of the gradient with respect to theta of log f of x. And this f of x is often given by an exponential. So if we think of the Boltzmann distribution, then clearly this function here with the Boltzmann distribution, this takes a simpler form, because then I have a log or an exponential. So that gives me simply the argument of the exponential, which then we have to take the derivative of. So think back of if it's a Boltzmann distribution, then this is given by e to the e of x of I of theta. And that means that I have to take the derivative of that function E with respect to the parameters of the network. So this quantity which you have here, this is nothing but, if we write it out now, I element of D, and then I have the probability distribution of theta, and then d theta, and then I have log of f of x of I of theta. And this is what we will typically write as the expectation value with respect to this probability distribution of delta of d derivative with respect to the variational parameters, or not the variational parameters, but the parameters of the network. So this is a quantity which we would typically evaluate with the Markov chain Monte Carlo methods. So this is normally then evaluated by MC squared, so which stands for Markov chain Monte Carlo. And when we approximate it like this is divided by the number of Monte Carlo cycles. So let me just write Monte Carlo cycles or samples, just samples. And then I have a sum over j. And these j's are now points which I would sample in this domain of configurations. And then I would simply sample this quantity f of x of I of theta. So this is the most common way by which we would sample this quantity. However, as you will see, this becomes a little bit less flexible and somewhat time consuming because this f is typically a multidimensional quantity. Now, since I mentioned Monte Carlo Markov chains, we need to say a little bit about those as well. So I'm just, yeah. So the J is, so this should be actually, it should be J here. J, yeah, sorry for that. This should be a J. So this is given by 1 up to the number of Monte Carlo samples which we are choosing. So this could be in the millions, or it could be in the thousands, etc., etc. So what we need to do now is just to give you a quick reminder of the mathematics of Markov chains and Monte Carlo sampling. And that leads to two central algorithms, one which is the Metropolis-Hastings algorithm, and the other one which is Gibbs sampling. And it's normally Gibbs sampling, which then, as we discussed before the break, brings us back to the conditional probability. Any questions so far? So this is one of the quantities we need to evaluate. So we will have that one. And then what we also need to evaluate in addition is obviously this quantity which we have here. But that quantity is easier when we have a expression or a model for this function f. So the tricky part has always been the evaluation of the normalization factor. And the way we rephrase that one is in terms of an expectation value. So we would then perform the sampling between, for different sets of x's. We would then calculate this one, but then we would also calculate the quantity which you see here for given x of I, and then subtract the two quantities. And that would then define the total gradient of the probability distribution. Okay. So we're going to dive into the mathematics of Monte Carlo samples, or that is Markov chain Monte Carlo. And many of you have seen this before, but I'm taking the liberty of just reminding you of some of the basic elements of a Markov chain. I hope you don't mind with that, that we are going to do that. So what I'm going to assume now is that I have my probability distribution, which we discussed, of a P of X of I, and that has now a dependence on a given variable T. So you could think of T as time, but I'm simply going to replace that one with a shorthand, which is a P of I here. And this is going to be a function of this variable T. So this is a probability which could be time dependent, but T does not need to be equal to time. We also have a normalization factor of T when I sum over all the possible samples which I have. So this is normalized to 1. Then I'm going to define a probability transition, or a likelihood for making a transition to a new state. And I'm going to define that by a matrix. And that matrix has elements ij. And I'm going to rewrite that one in terms of the probability of moving from a state j to a state I. So I am in a state j, and what is the probability of making a transition to that state I? So that is what this expresses. Now, a Markov chain makes the following assumption. So a typical assumption is that this probability distribution is time independent, but it could depend on the spatial positions where the particles are, or the objects which we are moving. So you don't need to think of T as time, but you can use that one as a way to increase the kind of how to say, understanding of what a Markov chain does over time. So what you would have then is that the probability P of I of given at a time T could now be given by the sum over all the probabilities of moving from a state J to a state I, multiplied with the probability of being in J at a time T minus 1. So this is the mathematical definition of a Markov chain. And it depends only on the previous step. So it depends only T minus 1. So all history before that is lost. Now, this probability transition, for making a transition, is, as I said, in this case, defined by a matrix. So what it means then is that we need to define a stochastic matrix. So if I sum over all the column elements, they have to sum to 1. So W is a stochastic matrix. Which also means that it has 1 as the largest eigenvalue. So largest eigenvalue lambda 0 is equal to 1. And what we have now is that lambda 0 is larger than lambda 1. And this is larger than the smallest eigenvalue which we have in the system here, which I'm now just going to label as an n minus 1. So I'm assuming now that W is a quadratic matrix. It's a stochastic matrix, so it can be normalized, and it has as the largest eigenvalue lambda 0. So we can also now assume that it has eigenvectors, since I can diagonalize the matrix. So it has a set of eigenvectors, V of I. And since I have diagonalized, these eigenvectors have to be orthogonal to each other. So what I can do now is to expand my probability P at T equals 0 can now be expanded in terms of the overlap. So I would have a P of I, and I'm summing now over all the coefficients here, V of I. So my probability at a given time, t equal to 0, can now be expanded in terms of the eigenvectors of the stochastic matrix. Now, when we have reached the most steady state, so just when steady state or most likely state is reached, and this is also called the steady state or the stationary state. What happens then is that this P of t is equal to P of I of t minus 1. And the probability becomes time independent. And P of I is time independent. So time in quotation marks here. That means that if I go back to the equation which I put up here, this equation here, I can rewrite this in a more compact vector matrix form. Yep. Say it again. Yep. So this alpha, which that is just a expansion coefficient, which is then the overlap. So if we now put in a j here, this is actually the overlap. Alpha of I is actually the overlap between these two coefficients. So which I write like a pj of v of I. So in principle, I should actually have an alpha ij here, just to indicate that that is specific for just one of the coefficients, but I just skipped it here. So when the most likely state has been reached, then this is the definition of equilibrium. That means that we will just be jumping in and out of this state, and hopefully there's only one of them. Then if I look back at this equation which you have here, and I write this equation in matrix form and vectors. So instead of writing the specific component P of I can now look at a vector P. So what I have then is that P is equal to W. So I'm thinking of these as matrices and vectors now, times P. So that's an eigenvalue problem. And you see that the eigenvalue is equal to 1. So this is an eigenvalue problem. With lambda equal to 1. And that is the largest eigenvalue. So which is the largest eigenvalue? Of this stochastic matrix W. So I don't know how much statistical theory you have, but this is a kind of a standard thing you will see demonstrated in textbooks on random processes, Markov chains, etc. So if we then go back to the equation which we have here, this one, then we can look at the time evolution of this specific quantity. So if we then look at the specific vector here, we know that this, let's now just don't put a constant on it. So P of t, suppose we have t equal to 1. That is the same as this sum over I of alpha I of v of I, these vectors. But now we are multiplying. So let me just put that one in here. So we have a W acting on this v of I. And that is the same as this sum multiplied with lambda of I of alpha y of v of I. Now I can act on this many times. So if I act on this quantity, so this actually is the same as T of T equal to 1, which is the same as acting with W on the original state. So that means that if I take a P of T here, that is going to be given by my function, my matrix, acting T times on the probability at T equal to 0. And that means that this is something I can then rewrite as a sum over these coefficients. And then I will have lambda of I to the power of T and multiplied with V of I. So I know that this can now be rewritten since lambda 0 is equal to the largest eigenvalue, and that is equal to 1. This is the same as lambda 0 to the power of T, which is equal to 1, multiplied with alpha 0 times V0 plus the sum over I equal to 0. And then I have my lambda I to the power of T, alpha of I of V of I. So how fast this goes to 0 depends on the next eigenvalues. So remember now that lambda I is the absolute value, is less than 1, and lambda 2 is smaller than lambda 1, etc. So that means that the sum which you see here, how fast that one goes to 0, depends on the eigenvalues of the stochastic matrix. So if they are well separated, this will quickly converge to the most likely state. If there is a certain likelihood of populating other states, then this convergence process will be much slower. Now, when it comes to this kind of Markov chains and Markov chain Monte Carlo, what you will often have then is something which is called a burn-in period. And the burn-in period is the one which defines how many steps you typically need to reach the most likely step. So you will often see in the Monte Carlo literature that people call these thermalization stages or burn-in steps because you need a certain number of steps before you have reached this situation here, where you are in the most likely state. And it's when you have reached the most likely state, that is when you start collecting your statistical quantities needed to calculate the expectation values. Because then you are in the most likely state and you will just jump in and out of the most likely state. So what you would typically see is something like this. So if you're calculating as given observable as a function of time, so suppose now that the exact value is this one. So you would start in the beginning somewhere here, and then after some time, it will just fluctuate around this minimum value. And then that means that you discard the type of steps you need before you have reached this most likely state. So you will often see that people use a variable called burn-in steps or thermalization steps if you're dealing with systems of finite temperature. And these are the steps which you need simply because you have to make sure that you are in the most likely state. You don't know exactly when you reach that one. You can have measures for that. But normally what people do is to have some kind of practitioner's feeling on how many steps you need. And some people put this to 1% of the total number of Monte Carlo samples, or you do 10%, and that depends a little bit on how conservative you are. You can calculate things like the correlation functions, which give you a measure on how correlated these data are. And that tells you that if the correlation function goes to 0, that is typically when these quantities don't fluctuate much. So these fluctuations will always be there because you will be jumping in and out of this optimal state, but you will essentially jump in and out around the most likely state, or what is normally called the steady state or the equilibrium state. Okay? So you've probably seen many of these things before, but I just wanted to repeat them because when we are going to implement a Boltzmann machine, these are quantities which we will be using. And the Monte Carlo sampling is a Markov chain sampling is the one which makes these type of samplings possible. Okay, let's take a look at the way we then accept the typical samples. So we have two ways to accept a new position, to accept a new value. X or Y. So one of them is called the Metropolis-Hastings algorithm. Which I know that many of you have met. And the other one is called the Gibbs sampling rule. So they are all, you should add to this Metropolis-Hastings sampling and Gibbs sampling. So let me remind you quickly of the pros and cons of these different methods. So when you're dealing with this type of sampling, one of the assumptions you're making is that you have reached something which is called a detailed balance. And in the Metropolis sampling, so let me quickly remind you of that. What we have, and this is one of the problems which I want you to keep in mind when we are running this type of calculations. So if we go back a little bit to the basic equation for the Markov chain, when you look at this equation here, what we have is a model for the probability distribution. So this is something which we know how to model, even if it's a complicated, multidimensional beast. However, even if we have that, this quantity here is often a quantity which we don't know. This quantity can represent complicated physical processes. And even if we could calculate it, it would be so difficult to evaluate from it that we simply don't want to deal with it. Now, one of the advantages of the Markov chain Monte Carlo procedure, together with either Gibbs sampling or Metropolis-Hastings sampling, is that we don't need to know the value of this quantity. So let me try to motivate why we don't need that value. So you see there are many bottlenecks here. And you would think that since we don't know this one, how can we calculate things at all, right? Even if we have a model for that one. So the basic recipe for doing this is often to make a model, since we don't know this W. So the typical approximation then, if we now look at this probability for going from J to I, so this is a transition probability. It represents the probability of making the transition, but also accepting the transition. So it's common to write this out in terms of a pure probability of making a transition. So this is normally called transition probability. And multiplied, so I have a probability of making a transition, and then there is a probability of accepting it. So what you see here is us making a model of something which we don't know. So in principle, we don't know what this looks like, and that obviously allows us to make a model for it. So you could even think that there are some physical processes which you can make a reliable model for. And then you would then you want to then estimate the acceptance probability. So this is normally called acceptance probability. So what you can do then in these type of machinery is the following. So in statistics, there's something in Markov chains. There is something which is called detailed balance, which has to be observed. And that means that you can set up the ratio between the probability in a new stage. So this is this quantity which you see here. This is the probability of having ended in a new state where you were in a state with probability P of J. So you can think of P of J as representing a specific position in space, and then you make a move to a new position in space, which is an X of I. So in that case, this is a quantity which you have this left-hand side is something we can calculate because we have an expression for it. So we made a model. So this quantity here is known since we have a model. Even if it's a multidimensional ugly beast, which takes a lot of time to sample from. Then, when we do this, we can actually set this up in terms of these unknown quantities of J to I divided by T of I to J. So this is the reverse probability. And it's common. So the simplest thing is to assume that this probability is reversible, which means that it's going from I to J is the same as going from J to I. And then what we have is that P of I, P of J is equal to A of J going to I divided by A of I going to J. This is something which is used to define the standard metropolis algorithm. And the reason why you end up with that expression is that, one, you would accept moving to higher probability. So we are actually maximizing a quantity, which is a probability distribution. So moving to higher probability is something which we would accept flatly. However, if you only move to higher probabilities, that means, so if you move to higher probability, so higher probability, or staying in the same place, that gives P of I divided by P of J larger or equal than 1. So staying in the same place when you suggest a move is also an observation. So if you stay in the same place, the ratio is 1. If you move to higher probability, you move to higher values larger than 1. So what happens then, and this is the metropolis algorithms, what it does, it makes an assumption. It makes an assumption that if these probabilities which you have here, they take values between 0 and 1, and it means that you put this one to the maximum value. So this is where you bake in a certain sense, your lack of knowledge of this probability distribution. So that means that if you do that, the metropolis algorithm that simply says that this probability of A of J going to I, accepting the move, so you're suggesting a move, is given by the minimum of 1, and then the ratio of these probabilities. Because if you only accept moves going to higher probabilities, then you will be stuck in one point in space. So you have to accept moves to lower probabilities. If you accept a move to lower probability, that means that this quantity is less than 1. And then you simply put this quantity to the maximum value, which is 1. So this is a way to optimize the way you jump into space. You can actually have other maximization criteria, but this has been shown to be mathematically the one which optimizes the way you sample the domain of possible positions or possible samples which you have accessible. So, however, the drawback with the metropolis algorithm is that we need to evaluate this ratio between probabilities. And that can be expensive computationally if you have many, many parameters. So what happens then is that this is often replaced by Gibbs sampling. And I see that time is running out now. So we will start with Gibbs sampling next week. This is a technicality. And then with Gibbs sampling, we are then going to set up the basic machinery for running a calculation with a Boltzmann machine. And when we are done with Boltzmann machines, which is next week, we are going to enter variational autoencoders. Then we're going to do generalized adversarial networks. And finally, we're going to look at diffusion models. And that is basically going to conclude the topic which we will cover in this course here. Okay. So thanks for coming to everybody. You will find the recording at the usual place.